Hello, everyone. Thank you for joining us for another live webinar session hosted by EE Tech and All About Circuits. My name is Dale Wilson, and I'll be your moderator. Today's session is brought to you by Advanced Cooling Technologies and is titled Mastering Heat Dissipation, Sustainable Strategies in Thermal Management for Power Electronics. Let me tell you about our two presenters. Brian Muzica is the Vice President of Sales and Marketing at Advanced Cooling Technologies. He holds a BS in Mechanical Engineering from Penn State University and a Master's in Business Administration and Engineering from Lehigh University. Brian has over 10 years of experience in both engineering and business development. He has worked closely with customers to tackle some of the most challenging thermal management problems in the defense, space, and industrial sectors. Our second presenter is Devin Pellicone. He is the manager of the Product Development Group at Advanced Cooling Technologies. He has a BS in Mechanical Engineering from Temple University and an MS in Mechanical Engineering from Villanova University. He has over 10 years of experience designing and building both passive and active two-phase cooling systems for a wide range of applications. Specifically, Devin has led two-phase cooling programs ranging in power from 100 watts to 100 kilowatts for industries like high-performance computing and power electronics cooling. Devin has 2 patents pending related to two-phase cooling products, and he has authored or co-authored numerous conference and journal papers on this topic. Following the presentation, we'll have a live Q&A with Devin and Brian. You can submit your questions during the session using the chat box on the right-hand side of your screen. We will also provide our attendees with a downloadable copy of the presentation once the session is completed. This will be available in the Resources tab, along with a few other links you can access at any point during the presentation. And keep an eye out for a poll that we'll have later in our session. Now, thank you so much for joining. With that, I'll hand it off to Brian to get us started for the presentation. Welcome, Brian.
Thanks, and appreciate everyone for joining us today. I think we have a pretty good session here and would certainly be interested in discussing your thermal challenges in more detail. So please ask questions. And if you don't get the information you're looking for, please reach out to Advanced Cooling Technologies after the session, and we'd be happy to go into more detail on any of the technologies discussed. So today, in terms of agenda, we're going to give a short introduction on who Advanced Cooling Technologies is. This is our first time doing a webinar with EE Time, so hopefully a lot of new audience and faces to ACT. So we'll give kind of a quick introduction on Advanced Cooling Technologies, and then we're going to dive into the details of system-level thermal design, challenges within the power electronics spectrum, and then potential thermal management systems and solutions for those challenges. And again, please ask questions as we go along. I think we'll have a good chunk of time at the end to answer any questions. So want to provide the feedback that's best suited for the audience here. So Advanced Cooling Technologies, we're in our 20th year of business. We're a small business out of Lancaster, Pennsylvania, currently slightly over 220 employees. And our focus is thermal management. So we do the entire gambit of thermal management from active to passive cooling solutions. We do everything from research and development through product development and through production. So we're a manufacturer. We're not simply a design or thermal analysis service provider. We do kind of the full spectrum of work. So really, we like to be very incorporated into our customers' needs and understand their system as best possible, so we can provide a custom engineered solution that meets your needs. And as we talk through kind of the industrial power electronics sector, you'll see a lot of the design considerations have to do with not only performance and environment, but also the economics associated with these designs. So we'll go through a lot of that in detail as we explore the technologies. But we do want you to view us as kind of a one-stop for all thermal management. So please bring us complex and challenging problems, and we'll have a solution for you. And kind of building on that in terms of our product portfolio, we'll only touch on a couple today. But again, we do have a lot of various options or tools in the toolbox to bring to our customer base. So we have passive solutions with enhanced conduction or passive two-phase heat transfer to really drive out the delta T's in your system or transport heat from one space to another. And then we're also very well versed in the liquid cooling side with more traditional liquid cooling and chillers to more advanced solutions like pump two-phase technology. And we do have experience in a wide variety of industries. So you'll see some different style of pictures, from very ruggedized defense to more commercial or industrial applications. So again, we can kind of handle a lot of the really complex thermal challenges, and then have kind of the portfolio of technologies to lean on as we start developing solutions for our customer base. So with that, we'll get into kind of the meat of the presentation. And again, this is focused a lot on power electronic systems. So, and somewhat of a focus on the industrial sector. So in terms of the challenges within power systems or power electronic systems, we actually did a short poll in the industry and came up with these as the critical criteria that designers are looking for. So the first one from a technical side is the heat flux. So there's been a lot of notes or trends in the industry that the heat flux at the component level is increasing, which will impact your junction to case resistance and then your overall thermal budget for your solution, but also the power densities within the system in general. So again, creating a higher heat load to put the onus on the thermal management system. The second area is compact designs. So whereas if you had unlimited space and volume, which we all wish we did, it would be fairly straightforward to design a thermal management solution that can meet your goals. But in most practical applications, we're designing to a constrained volume or a constrained weight factor, and need to design the system appropriately. So compact design is certainly a big consideration, and you'll see various examples of unique form factors to consider as we're going through the technologies. The next one here is cost per kilowatt. So this is a term we hear a lot from our customers, and really this is kind of looking at the initial investment cost. So how much does your thermal management system cost, and how much heat can it reject? So with those two factors, it kind of is a cost per kilowatt analysis for the initial investment. And again, the solutions we're looking at are trying to position themselves for these more industrial commercial markets. So inherently, there is a cost benefit. We're not using anything crazy or complex. It follows a lot of the general guidelines or rules of thumb that have been established in the industry. The next area is reliability. So one of the challenges as heat increases in your system is you start going to active systems, and you start introducing mechanical components, failure points, electrical systems. And so there are reliability concerns, but to kind of assess it, we look at the various componentry and try to create the most reliable solution based on the mean time between failure or maintenance routines that need to go along with the solution. So reliability is a key aspect, especially if your system is going into more of a remote location and is not easily accessible. So we understand and work with our customers on those type of situations where reliability might be a higher in the trade hierarchy. And the next one is electrical isolation. So as you start dealing with medium or high voltage drives or systems, it becomes a kind of a safety, intrinsic safety matter to make sure that your thermal management system does not introduce any safety risks or shortage risk in your system from an electrical perspective. So a lot of what we'll talk about there is the use of dielectric fluids and refrigerants to combat that challenge. And the final bullet, as a lot of our customers make us very clear on, is the lifetime cost and ownership of thermal management systems. So whereas the cost per kilowatt is typically an initial investment analysis, the lifetime ownership takes into consideration your maintenance cost over time, your replacement cost over time, as well as your energy consumption in these systems. So we'll look at kind of all those different avenues as we go through the presentation and look at different technologies. So this is kind of just a summary of what we just went through, but when we're talking about thermal solutions or thermal systems, really what we're looking for is something that's not going to be eating a lot of energy, because you want your overall system to be cost effective long term, and you don't want to have something that's using a lot of energy to run your thermal management system. In many cases, the thermal management system could be utilizing similar orders of magnitude energy that you're trying to cool down. So it does create somewhat of a compound problem as you start analyzing your thermal management system in conjunction with the overall heat rejection requirements. The next is low maintenance required, again, to drive down that lifetime ownership cost. Low initial investment with the cost per kilowatt. Scalable solution. So this is one that every product pretty much that we'll talk about, especially the dielectric-based passive and active two-phase technologies, are going to have a scalable component. So they're very scalable, and we'll show examples of rejecting a couple hundred to a kilowatt worth of heat, all the way up to a couple hundred kilowatts of heat with the same technology, and just scaling the form factor. And then again, we'll look at ROI and levelized cost of energy, the LCOE of these various technologies. And again, just looking for the implementation and usage to match kind of the economics with the system. So here's a kind of a snapshot of more of a grid tie application, but kind of as we go through the technologies, we want to kind of throw the onus that there is a lot of technologies, a lot of thermal solutions being offered and serviced in a lot of these systems, and sometimes they communicate and work very well together, and other times they're piecemeal together. So as we look at things and talk about different technologies, it's also good to have a very complete site-based or system-based approach, because a lot of times you can combine technologies and really drive down those areas we're talking about to provide long-term value to your customers and our customers. So with that, kind of just summarizing what I went through, but what we have seen, and hopefully what we'll portray in this presentation, and what we want you to think about as you're considering some of the options we're talking about, is again taking more of a system level look at the thermal challenge. So in many times, if you're putting together various thermal technologies, or if you're looking at one area and then moving to another and having isolated thermal systems, you're actually adding a lot of cost and complexity to your design that could be reduced by taking more of a holistic approach. So at ACT, we like to take that kind of ask a lot of questions to our customers, really try to understand the system parameters, so we can come up with a thermal management system that creates that long-term benefit for our customers. And with that, we'll jump into kind of the technologies and solutions that we talked about. Here's kind of just an overview of the presentation and how we'll progress. So in most cases, we'll be focusing on direct cooling, where the thermal management system couples with the heat sources directly, and then transfers and rejects heat to either downstream or within the thermal management system. But we'll also look at enclosure coolers initially. So these are more low to mid power cabinet coolers, and their big value add is it's circulating air while maintaining a seal. So it keeps everything kind of clean in your cabinet, but does provide air circulation to take heat from the components and reject it to the other side of the cabinet. So starting there, this is more of a kind of product offering slide as opposed to overview of this technology, but we'll go into some applications in the next slide to talk about where and when you might want to use these and the background technology that goes into them. But in general, we have two product offerings for enclosure cooling. And again, these are solutions that couple onto your cabinet that you can kind of see there on the left side. And it does provide a NEMA or IP rated seal, and it exchanges heat between the inside and outside of the cabinet. So there's two kind of categories of cooling. One is above ambient cooling, where you don't need to cool your cabinet below the ambient air temperature. So there you can simply exchange heat through above ambient coolers. So The one you're seeing to the left is called our heatsink cooler, which just relies on circulating air inside the cabinet to collect the heat, conducting through a baffle plate in the middle, and then another fan on the outside to reject the heat to ambient air. So a fairly straightforward technology and more of an economical solution for customers. But again, in these cabinets, it's usually not a ton of heat. So solutions like this can reject the heat load and be kind of a drop-in replacement for what's going on in your system. The second one in the above ambient is our heat pipe cooler. So this one is a top-mounted solution, and it actually uses heat pipes within the core of the heat exchanger to effectively transfer that heat. So again, it's circulating air inside the cabinet to collect the heat, but the heat pipes are doing the work to transfer heat to the outside air. And by having that improved heat pipe conduction area, it allows you to have a much more compact design. So if you can mount on top of your system, you can get away with a good amount of heat rejection in a compact form factor with heat pipe coolers. And then the sub-ambient cooling options, there's again 2 options within that spectrum. So if you do need to keep your cabinet lower temperature than your air, the 2 options outlined here are the ones on the left is the thermoelectric cooler, and those use Peltiers or thermoelectrics to provide that solid state cooling. And on the right is your more traditional air conditioners using vapor compression to provide the sub-ambient cooling. And again, these options are all designed to maintain a seal. So the goal of this product line is really to create a clean, cool environment within the cabinet. So if you're in a harsh environment, outdoor, or a very dusty indoor manufacturing environment, it's a really good solution to fairly straightforward, keep your electronics cool by circulating air and taking the heat outside. And just to go to a couple application details on this technology, again, you can see for customers, it's a fairly straightforward implementation. We do provide all the details of these coolers on our website as far as how much heat they can reject at a given delta T. And we also provide the cutouts and drawing patterns so that they can easily install them into your cabinet. So on the left photo here, this is an outdoor drives cabinet, and this was our HSC 68. So it has 3 different heatsink fan combinations on it. And then what you're seeing kind of overlaying on top of the fans is a rain guard for outdoor use application. So again, the customer came to us, specified their heat load in the cabinet and their environmental conditions, and we're able to quickly direct them to a product that would work based on those areas. The second one here in the middle, this is our heat pipe cooler. So on the bottom of the picture, you can see kind of a cross section of the heat pipe cooler, the HPC, and in the copper color, you can see the heat pipes kind of shown there. So the heat pipes are simply straight heat pipes using methanol as the working fluid, and they're going to transfer heat from the hot air inside the cabinet to the cooler air outdoors. And heat pipes, as we'll get to in a couple slides, is an extremely efficient mechanism for transferring heat. So able to transfer heat at a very low delta T, and again, driving down that footprint of cutout needed on the cabinet. And the example you're seeing there, that's hard to tell exactly where it's going into, but it's a machining factory. So that's going on top of a electronics enclosure that's driving the machinery. And then the final one to the right, this is our vapor compression cooler. So again, more or less an air conditioner, but designed to be fairly narrow so that you can mount it like you see here on a door mount in an electronics cabinet. That a lot of time is preferred because it's usually space that's available and not mounted with electronics and other insulation and everything. So we do have a lot of door mount applications, and you can see there, again, a fairly straightforward cutout and not a lot of intrusion into the cabinet. And our vapor compression coolers run from about a kilowatt to 5 kilowatts of heat rejection at a 0-degree temperature gradient. So fairly good capacity for their volume, and again, very easy installation. And I guess just one more thing to mention about our enclosure coolers. They are off-the-shelf products, so you can order them online. And there's also a calculator on our website, and that actually allows you to put in all your various inputs of your environment. So whereas a lot of times if you're operating indoors, it's a fairly straightforward calculation on the amount of heat you're generating and your indoor air temperature. If you're in an outdoor environment, you have to take things into consideration like solar loading and things like that. So we do have a calculator that provides all those details and will output a product that'll work for you. So yeah, please feel free to play around on our calculator and see if there's a solution that matches. And if not, we could look at some of the technologies we'll get into in the next couple slides. So we talked about enclosure coolers as kind of your air mixing solution. Now we're going to talk about some of the methods for direct cooling. So again, direct is more or less when we're contacting with the electronics directly and then moving that heat away to some type of ultimate heat sink. So the first technology we're going to look at is heat pipe technology. This has been utilized for many years, and I'm guessing a number of the audience is familiar with this technology, but it's an extremely effective heat transfer mechanism. So how it works is you have an evaporator, which shown in this picture is one end of the pipe, but it doesn't need to be an end of the pipe. It could be anywhere that you're introducing heat along the length. But at the evaporator, that's where you'll couple it with your heat source. It'll take in that heat, vaporize the working fluid, and that heat source will create a pressure and temperature gradient within the pipe that'll push the fluid vapor to wherever it's colder in your system. In this example, on the opposite end, which would typically be coupled to a heat sink. And at the heat sink or the condenser end, it would give up its latent heat, condense back into a liquid. It would be trapped within the wick structure. So on the inner diameter of the pipe, there's a porous wick structure that absorbs the liquid and then passively transfers or pumps that liquid back to the hotter region. So again, it's a fully closed loop system that simply operates with the pressure and the temperature gradient. So it provides extremely good heat transfer because of the latent heat of vaporization, but no moving parts, no mechanical actuation. So it is a very reliable and long-lasting solution. And from a thermal standpoint, it operates with about a 2 to 5 degree temperature difference across the length. So as you're considering this compared to like a metal conduction, you can see how you can kind of very easily short circuit the conduction delta T by implementing a heat pipe. And now we'll kind of look at that exact example that I just mentioned. So in many cases in the power electronics world, the goal is to eliminate hotspots. So one of the areas that we've explored a lot is embedding heat pipes into metallic plates, and in most cases aluminum, because it's fairly cost effective and already has some good thermal properties. So by embedding heat pipes into aluminum plates, you can increase the thermal conductivity of those plates by a couple of factors. So aluminum is typically somewhere between 150 and 200 watts per meter K. By implementing heat pipes, you can easily achieve 600 watts per meter K. And in certain cases, if you have long distance heat transfer, you could achieve over 1,000 watts per meter K. So an example of that, as you see on the bottom left figure, these are kind of a single metallic IGBT cooler. So a single IGBT was mounted to those systems. In this thermal model, we used the inputs on both the left and right. The right one was the pure aluminum, and the left one was after it was integrated with heat pipes. And you can see kind of the hotspot elimination there. So the heat pipes with that 2 to 4, 2 to 5 degree temperature gradient along the length of the pipe will spread that heat to the extremes of the heat sink. So not only are you eliminating the hot spot and reducing your case temperature of your electronics, but you're getting better fin efficiency from the outer fins in that scenario. So yeah, that's one example that you can see there from a thermal analysis standpoint. And then on the right side, 2 examples of fielded hardware for this exact scenario. So these were both IGBT cooling applications. The top one was a naval power electronics cabinet, and that one had multiple IGBTs mounted to the backside of what you're seeing here. And it's a little hard to tell, but the fins that you see there are very tight pitched. So this one actually had a high airflow going through those fins, so we're allowed to get a lot of surface area and space those fins out very, very tightly across that. So a very compact design, but again, isothermalizing that entire base and getting the best use of all those fins in there. And then the bottom one, same example, same story, but in this case, it was a natural convection heatsink. So you can see a much more spaced out fin set. And in this application, they also had a fairly uneven distribution of the heat source. So on one fin stack was actually coupled with about 80% of the heat load. So one fin stack was doing a lot of work and had a large delta T, whereas the other fin stack was not doing as much work and was keeping items cooler. So overall, the system had enough fin area, but was still getting hot spots. So what we did is just embed heat pipes underneath those fins and basically exchange the heat. So again, smoothing out that heat load that each of the fin stacks had to deal with and reducing temperature of the overall conduction gradients and the case temperature. So that's kind of the heat pipe side of things. Another passive two-phase solution, kind of a variant off heat pipe technology, is thermosiphons and then loop thermosiphons. So thermosiphon is the name for a gravity-assisted heat pipe. So in those cases, you do not need a wick structure to return the fluid. You're relying on gravity to return the fluid. And in those cases, it can be very similar. A thermosiphon can be very similar to a heat pipe, just unwicked, and knowing that you need to couple your heat sink above your heat source. So if you have that scenario, you can use thermosiphon technology and get the benefit of the gravity assist. What ACT developed and is implementing in the field is loop thermosiphon technology, which takes it to kind of a higher or more advanced level and enhances your heat transport capabilities even further. So same design principles or considerations here. You're evaporating at your heat source and you're condensing at your heat sink. But because you're running in a full loop and it's designed strategically that when you're condensing, you're continuing the path of the loop, you never have the forces interacting. So your vapor is flowing one direction, your liquid's flowing continuously along the loop. In a heat pipe or a typical thermosiphon, those forces would interact. So your vapor would be flowing down the center and your liquid would be returning around the outside, but that creates some inertial forces within it, which limits your overall capacity. So in the case of a loop thermosiphon, you can move more heat in a similar form factor. Again, other benefits is you can have very long distance heat transport as long, again, as your condenser is above your heat source. It's also a fairly scalable design, and you can have multiple components. And you'll go into some examples where you'll see multiple components mounted to a single evaporator, and the ability to scale this technology from a couple watts to a couple hundred kilowatts. So a very scalable technology that we've demonstrated. And then looking at some examples here, the top one there is a medium voltage drive cabinet. So this had kind of the example I was alluding to, multiple high powered sources on that single evaporator plate. So the metallic kind of silver aluminum plate that you see there coming vertically had 6 heat sources mounted to it, so 3 on one side, 3 on the opposite side. It used refrigerant as the working fluid, and again, transferred that heat in kind of the schematic you saw on the previous slide to an air-cooled condenser. And this one had a fan coupled with it and utilized that heat sink that you can see there with some horizontal airflow. This very similar design can be very flexible, so we can do it with a vertical airflow. We can also do it with a remote condenser with some flexible tubing. So again, a very flexible design as long as you have the condenser above your heat sources. So that exact example, you can see kind of some of the figures there, but had an extremely low thermal resistance, so very low temperature gradient across those areas. And we were able to operate that system between -55 and +50 degrees C and transfer and reject over 11 kilowatts of heat. So a very capable solution in a fairly small form factor. That entire solution fit within kind of a medium voltage drive cabinet with only the condenser exposed to the air environment. And then the bottom solution here, similar type application. This was a 5 to 10 kilowatt cooling capacity. But what we're showing here specifically is the orange hosing that you see. And this was somewhat of what I was alluding to in the last example as well. But you have the ability to have a remote condenser and flexible lines between the evaporator and condenser. So this allows for designers of these cabinets to integrate thermal solutions late when it's already fairly populated and packaged. Also allows you to run fairly long flex lines. So if you didn't want rigid tubing in your system, to allow for you to integrate, manipulate, maintain, clean the cabinet, you have that ability and that flexibility there. So again, fairly scalable design and a lot of different form factors we can work with here. Devin, anything you want to add?
I'll just add on that bottom picture there, those orange hoses are high dielectric strength hoses. So for applications where you want to, say, float your modules at the potential of your system and isolate them relative to the condenser, which may be at ground potential, we've demonstrated the ability to stand off 40 plus kilovolts per foot of voltage with this type of solution. So you can get high heat dissipation and maintain isolation between different phases of your system or between an individual phase and ground with a solution like this.
Awesome, thank you. So, heat pipes and loop thermosiphons are both fall into the passive heat transfer technology spectrum. So now we're going to flip it to an active cooling. So at a certain point, air cooling or passive solutions are not going to be an option due to the either growing heat flux or overall power of the system. So designers will have to move to a pump liquid solution. So I think a lot of you, if you deal with cooling on a routine basis, are familiar with pumped liquid solutions and single phase solutions. So our focus of this presentation, and probably where we'll spend a good chunk, is on pump two-phase technology. So a lot of benefits that we're showing here, I guess just to kind of couple on some of them, is again, the intrinsic safety with the dielectric working fluid. So if you were, one of the biggest concerns of a water-based liquid solution is if you do spring a leak, you are going to damage all your electronics and kind of have to start from scratch. So in these systems, you're actually not using a ton of fluid because you're running at two-phase, again, taking advantage of the latent heat of vaporization. But if you do have a leak, it'll kind of dispel refrigerant in vapor form, and it'll be fairly, it's dielectric, so it won't damage your electronics, and you'll have ways to monitor the system so that you can safely shut down and save all the electronics and just fix the leak and go from there. Some other benefits is it's hot swappable, so the usage of quick disconnects and being able to insert and exert different componentry while the system's fully charged is a big benefit. And you'll also see some of the things we mentioned earlier. It allows for a compact system because you're running at a fractional of the horsepower of the pump compared to a single phase system. So a lot of benefits you have here. There's also thermal performance benefits, higher heat flux and isothermality. So what we do at ACT is kind of take the system design parameters and come up with a solution that'll create an economical design for whatever situation you need. So in certain cases, we have to design to the extremes of isothermality and safety and performance. And in certain cases, we're only designing to one or two, but we're not going to over design the system. We're going to work with you to come up with the ideal solution. And just to look at the top right figure, again, comparing it to a single phase system, very similar componentry. So a lot of times one of the earlier questions is, what is the cost of the system? And it's challenging to say because pump two phase is a fairly new technology, but the componentry from that standpoint is very similar to a single phase system. So usually we can replace a single phase, create a higher performing pump two phase system with basically just the addition of NRE to develop the system, not changing the overall long-term installation cost. But just to kind of run through the loop there, you have your cold plate or your evaporator. That's where you are coupling to your power electronics and you are vaporizing the fluid. That fluid vapor is then pumped at some quality, so it'll be a portion liquid, a portion vapor, and pumped throughout your system to the condenser, where it'll, again, give up its latent heat, condense back, and enter an accumulator. The accumulator is sized such that you ensure that you have complete liquid before entering the pump, and then you use a pump to create that pressure head. So we'll talk about all the different components as we go through the system, but it's a fairly straightforward loop, and then we add complexity as we get into the design considerations. So this slide kind of gives a view of the circuitry that goes on in one of these systems. So in many cases, and as we'll describe in the next slide, you have a coolant distribution unit, which houses your balance of plant or your componentry that drive the pump two phase system. And then you have your evaporators within your, in this case, an inverter cabinet or an electronics cabinet, which are coupled directly to your power sources. But as you can see here, it's a very capable technology when you're considering things from an entire rack or system level, because you can have multiple parallel evaporators. You can also have direct liquid evaporators, as we're showing with the power electronics here, or air to liquid evaporators, as we're showing with like the magnetics or the coupling of all the heat through airflow in the cabinet. So a very capable technology, and we can interact these systems with quick disconnects so that it allows you to easily swap out electronics or swap out CDUs, and makes it for a really nice long-term solution. Devin, you want to add anything here?
Just again on the dielectric portion of the loops, which is really what's enabling this. If we had a non-dielectric or a conductive fluid, we wouldn't be able to send the fluid through all of the individual components in, say, an inverter cabinet in series or parallel like this, because we'd be connecting them electrically. So the fact that the system's dielectric and can service multiple different types of evaporators makes it really attractive for applications like this, and we found wide use of this technology in the power electronics industry like this.
So now we'll go through a couple real world examples. The first one we're showing here is similar to what we just showed on the previous slide, but looking at a CDU with an air-cooled CDU, and then an inverter cabinet which has kind of plug-and-play cold plate or evaporator assemblies. So on the left, you can kind of see the system laid out from a CAD perspective, and then on the right, you see some hardware associated with it. So the air-cooled units, the air-cooled CDUs there, The top portion is the condenser, so that's kind of similar to your home HVAC condenser, but that was sized to reject 30 kilowatts of heat. And then underneath that, you can somewhat see, but you house your balance of plant, so your pump, your accumulator, and the other component of the CDU. And then not pictured on the hardware side, but just a picture of the evaporator plates. You can have those rack-mounted evaporators coupled, and we would deliver the trays to our customers, so they're just mounting their componentry on it. And again, it could slide into your rack with quick disconnects for very easy integration and service. Another example, this one kind of similar in form, but this one was a much higher power application for a data center. So maybe starting on the top right figure, this is the CDU. So this is a 200 kilowatt balance of plant. You can see the N+1 redundant pumps on the bottom. The accumulator is the large black container in the center. And this one, instead of being air cooled, had a liquid to liquid heat exchanger up top. So it was using facility water as the ultimate coolant there, and had a liquid heat exchanger to exchange heat between the dielectric refrigerant and the facility water. From there, the CDU provided the the fluid to the data center blades itself. So you can see the rack to the far left, and then the individual blades you can see on the bottom of the screen there. So all of those operated in parallel flow between blades and between the different blades that went into the server, and then serial flow within the blade. So each blade had 4 different evaporators on it, but the entire system ran in parallel flow. And again, 200 kilowatts, fairly complex circuitry, but the pump two-phase solution does allow for you designing in a lot of parallel flow channels, and as long as we understand what the end use is trying to do, we can develop it so that it can be controlled passively in most cases. And Devin, maybe I'll have you run through this one.
Sure. This is a another power electronics case study. This happens to be a DC-DC converter. So it was a medium voltage system, and it needed to supply plus or minus 6 kV DC power to the system. The big thing here is a couple of notes. There were 12 individual power blocks, 12 individual cells filled with power electronics. Each one of those cells was cooled by a central cold plate. So there are modules mounted to both sides of the cold plate and then packaged within a box that had the supporting electronics all within inside of it. And then 12 of those populated inside of this box to get a really dense type of package for this DC-DC converter. It was all serviced by a central pumping unit, which is shown on the right there, similar to what Brian was showing on the previous slide for the CDU of the data center application. This was a CDU for this particular power electronics application. And then in the back, the picture on the left, we're showing the manifold distributing the liquid and collecting the vapor from each of those cells. And again, we're using those orange hoses here you saw on some other slides. So this was able to stand off the 40 kV of required voltage between parallel sides of the system. So any one of those cells needed to stand off up to 40 kilovolts of isolation in a fault condition. So this is another application where we needed high dielectric strength, lots of parallel evaporators, and a really high power dissipation, which we're not sharing on this slide for proprietary reasons, but a very high type of dissipation out of a single cooling unit.
So with that, just some pump two-phase design considerations we wanted to share here. And we will start to speed up. We have a couple of slides left and want to save some time for questions. But yeah, just wanted to show some of the design considerations. We haven't gone a lot of detail in evaporator design, but those are specific to pump two-phase systems. So we need to kind of entice the boiling effect within the evaporators. Probably one of the bigger areas in the design phase is the flow balancing and parallel evaporators, as well as the balance of plant. So that's where we need to ensure all our componentry is working together. And sometimes these have fairly complex control schematics or systems based on what the end use is. Sometimes they can be completely passively controlled, but ACT does have both the thermal know-how, pump two-phase know-how, as well as the electrical side to create those control systems. And then we didn't talk too much about component selection, but pumps are obviously one of the more critical design. So we are selecting those for their ability to handle low viscosity fluids, as well as operate with minimal net positive suction head. So we need to kind of create a pump that meets the pump two-phase requirements, and then we'll select based on availability and cost. But most of the time we are designing with off-the-shelf pumps that are readily available. And then we're just going to kind of transition to one final technology to introduce somewhat of a new breakthrough that ACT has been working on. But before that, we want to just kind of introduce liquid cooling with the utilization of chillers. So many of you are probably familiar with chillers if you're utilizing any type of system that requires holding fluid at a given temperature. But the chiller is basically a vapor compression system designed to subambient cool or hold temperature where it's needed in the system. So similar loop as to what we've shown before with the introduction of a compressor to provide that subambient cooling. So again, we're not going to go into a lot of detail on chiller design. It is part of our product offerings, but we're mainly just kind of introducing the technology to show a hybrid product with chiller and pump two-phase. So yeah, I guess one more slide to show that chillers can be used in any environment. So we showed kind of more of an industrial one on the last slide, but we have developed these systems to go into very high shock, high vibration, hot conditions. So these are just a couple examples of defense applications, but whether it's a defense application or a dirty industrial application, we work with our customers and design some of the most rugged chillers that are available on the market. And yeah, with that, we want to kind of introduce, this is a current effort that ACT is developing using IRAD funding. And the goal here is to create energy saving subambient cooling options. So in most vapor compression systems, the compressor is the big energy consuming part of the system. And there are ways to shut down or turn on based on different conditions, but there is an ideal area where you can combine vapor compression systems with pump two-phase cooling and take advantage of pump two-phase anytime that you don't need that critical subambient cooling, and only turn on your compressor when your above ambient cooling is not available, when it's hot or sunny out. But in most cases and in most applications, pump two-phase can be used a lion's share of the time, and you're designing a vapor compression system for that one use case that happens maybe a couple times a year or one time a day, but you're really using a lot of energy to run that compressor all the time, whereas a coupled system using both the active and passive side of things can help reduce energy long term. So maybe, Devin, if you could run through a little bit of the background here.
Sure. So the idea is that we have a traditional vapor compression system where we compress vapor, expand it to get our cooling. That goes through a regular air conditioning coil if we're doing air cooling, where you blow that into your space and you get cool air like your air conditioner at home. For the applications or the times of the day when the outside air temperature is sufficient to cool your inside space, so cooler than your inside space needs to be, we turn the compressor off and circulate the refrigerant with a pump instead. So it just becomes a pump sort of liquid loop. We pump the fluid through a heat exchanger that you blow air across, then that fluid picks up the heat, dissipates it to outside air. The reason you would do this is for applications where you can't just open the window. So another way to do this would be turn off the air conditioner and just open a window essentially, or open up a louver. There's a lot of applications where the environment's dirty, dusty, toxic, corrosive. Lots of reasons you wouldn't want that outside air inside of your system. This is where this solution really shines. So you get the eco mode, the energy savings of the outside air when the ambient's sufficient, and the sub-ambient cooling for those hotter days of the year, all within one nicely packaged system.
So yeah, I think that covers our presentation. Apologize, we ran a little long, but we still do have some time for questions here.
Okay, let's get started with some questions. First one here is there a way to modify the capillary pump for the different zones in the heat pipes, like having different structures of wicks along the heat pipe?
I think the short answer to your question is yes, we can put different wicks inside of the system. We'd probably need to understand why this would be required for a particular application. Normally we size the wick structure for the worst evaporator that is in the system, or the worst case component, let's say, in the system. So they're fully custom components. We build it all in-house. So we do have the ability to put different capillary structures in there as required, but it's not often that we find the need to do that.
Okay, next one is, what is the highest temperature gradient you can go on the vapor compression cooler, and how will this impact the capacity?
Yeah, for all of our vapor compression coolers, VCC units, we have spec sheets on our website that you can look at, and there's various curves on those spec sheets for the different gradients. I believe we go up to 20 degrees C difference between inside and outside air temperature, and the capacity definitely reduces as you increase the gradient. So they're all rated at a 0 degree gradient between outside air and inside air, and then the capacity drops off a little bit as you increase that gradient, and the capacity increases as you decrease that gradient. So we have those values all tabulated and shown on a chart for each spec sheet of our vapor compression coolers. I would encourage you to go take a look.
Okay, and this one talks about 1U chassis. It says that our projects involve high heat loads stuffed into 1U chassis with limited airflow. Do you have examples of using heat pipes or thermal plates to move heat where an internal fan can be more effective?
Yeah, this is a great use case for heat pipes. We often will embed heat pipes into systems where there's no immediate volume to dissipate the heat at the component or in the chassis. We'll use the heat pipes to move the heat to other areas where volume may be more available. Or in some of our avionics 1U chassis, we'll move the heat across the components to chassis rails where you can then cool the chassis directly. So that's a great application for heat pipes. They really shine in moving heat from A to B with minimal temperature gradient. So you can get that heat out of really tightly packaged areas and located in an area where we have more volume to dissipate the energy.
Yeah, and I'll add, we're also seeing in certain high power applications where you could potentially add a little angle and then run your condenser vertically on the back of the chassis. And then utilize a loop thermosiphon design. So for even higher power applications, that might be applicable there if heat pipes have some of the limitations.
And this question is about the high K plates. Are they custom or are there standard sizes available?
They're all custom. We do make a number of somewhat standard conduction card sizes for high K plates for avionics applications, but the vast majority of our high K plates are custom to the application. And the reason being that each application has different concentrated heat loads. And so we try to populate the heat pipes in the most densely heat absorbing areas so that we can better effectively spread that heat. So it's all custom to the application and the specific requirements of each customer.
Okay, and if you put the heat source in the middle of a heat pipe, will it work anyway? Will it be less effective? And how do you use the calculator as far as looking at how to put the heat source in the middle of a heat pipe? So I think talking a little bit about the fundamentals of a heat pipe.
It's a great question. Yeah, Brian alluded to it a little bit when he was talking about how a heat pipe works, but you can put the heat source anywhere along the length of the pipe. And if you put it right in the middle, that's fine. Everywhere where the heat is not being input, it's considered the condenser portion of the heat pipe, so it can be dissipated. So if you put the heat in the middle, we have the two ends to dissipate the heat from. We do that often. If you're trying to use our online calculator to figure out how that may work, you basically just take half the length of the heat pipe. So the effective length of the heat pipe is the distance between the point where you put heat in and the point where you reject heat. We call that the effective length. So if you're going to put it right in the middle of the heat pipe, then just take half the heat pipe length, and that's how you would run our online calculator.
Someone asked, how do I know that passive solutions will not work in their system? How do I know the limit that I need to move up to an active solution?
That's a great question. There's no fixed answer for that. One simple answer is that a lot of our passive solutions have a gravity dependence to them. So if you have a particular application where you know you have to move heat against gravity, so the heat is on the top and your cooling is only available on the bottom, that eliminates a handful of passive solutions that are available. Heat pipes are still on the table, but a lot of the loop thermosiphon solutions are not. So just by geometry, you may be able to identify if active or passive is required. Other than that, we now with loop thermosiphons have the capability to do very large amounts of energy transport, even passively. So we've demonstrated these gravity-driven systems that have no pumps in them doing tens, almost hundreds of kilowatts of heat transport. So that's not a factor anymore. It comes down to more the geometry of your system. So in those particular cases, we'd probably just have you reach out to us. We'd look at your challenge and advise from there.
Okay, and it looks like one more. Are there any options for maintaining electrical isolation between power modules with a single cooling solution?
Yeah, we talked about this a few times in the presentation. The pump two-phase systems in particular, and some of our gravity-driven two-phase systems use dielectric fluids that don't need to be actively deionized like deionized water would have to be. So they're dielectric and they stay dielectric, and then we use dielectric hoses in our system to make sure that we can isolate high voltage and ground potential components in the system, dissipate the heat from one to the other without connecting them electrically.
All right, well, thanks a lot. We did have one late one come in. I hope you guys can hear me now that I've tried to fix my audio issues. And special thanks to the Advanced Cooling Technology team jumping into the questions. We had one more audience question to come in. Let's get to that real quick before we close up for the day. Before I ask that, I will remind everyone that the handouts are available now. If you look at the upper right, click on that handouts tab and you can download the presentation and some other helpful information. So this last question, what are the high temperature limitations of heat pipes or thermosiphons? Are there any extremely high temperature solutions?
It's a great question. There are. In fact, we routinely make heat pipes that range in temperature from negative 100 degrees C all the way up to positive 1200 degrees C. In those extremely high temperature ranges, the working fluids are no longer things like water. They're now liquid metals. So alkali metals like sodium, potassium, cesium, sometimes lithium. We manufacture a lot of these heat pipes for portable nuclear reactors, space nuclear reactors, and calibration industry. So there's lots of options up in those high temperature ranges that use high temperature nickel alloy materials and alkali metals to achieve the same purpose of a heat pipe for an electronics cooling application, but much higher temperatures.
Awesome.
Yeah, I'll also add that we do have a fair amount of experience with like petrochemical type applications, and there are not only what Devin was talking about with the different fluid options, but different coating options on the heat exchangers to survive those type of like corrosive environments as well. So yeah, if there's a specific use case you're thinking of with that question, please reach out and we'd be happy to discuss further.
Yeah, Brian, Devin, thanks for that great presentation today and the awesome Q&A session. And thanks to the audience. You know, we had a lot of great questions today. We really appreciate your participation. And as Brian just said, reach out to them with any questions you have or help with your designs. They'd be happy to support you guys. Now, everyone, in just a moment, you'll be redirected to the industry webinars page on All About Circuits, where you'll be able to view this session on demand, along with other recent webinars that are readily available. Thank you for your time, and we look forward to seeing you at another live session again sometime soon.